Alright, today we're going to be exploring recursion in Python. In the last few videos, we covered how to interact with files in which we could read a file, write to a file, as well as append to a file. So now we'll be exploring the concept of recursion. Recursion is a concept that may be confusing to a lot of people at first, especially when it comes to writing your own recursive algorithms. But slowly as you start to write more and more recursive algorithms, you sort of get a sense and an idea of how the process actually works, as well as writing your own recursive algorithms to other problems. So a critical aspect of recursion actually comes through its step-by-step analysis. So if you understand and analyze each individual step of the process of recursion, then you'll slowly get a grasp and an idea of how recursion actually works and how you can implement your own recursive algorithms to a variety of problems that you can find. So what exactly is recursion? Recursion is a process of a function that calls itself over and over again. The recursion consists of a base case and a recursive case. So the base case is basically the simplest condition that you can find in regards to a problem, and it is also the termination condition for when the recursive process should actually stop. The recursive case is when the function is calling itself over and over again. So that's basically why it's called recursive case. It goes by the name recursion, in which a function is basically calling itself over and over again. So the way we notate this in Python is first we define a function, right? So the way we define a function is we have def. So we have def meaning define, and the name of the function, so I'm just going to say function as a format. You sort of get an idea of how you format recursion in Python. And so since we have a def function, this is supposed to be a code block, so we end this with a colon. If you give a new line, then it should give us an indent. So the way that we actually make the recursive call is calling the function by its name within the defined function. So this is how a recursion works. We have the defined function, and somewhere in this defined function is what we're calling the function by its name. So since the name of the function that I'm defining is function, somewhere in this function I'll be calling function by its name. And that's basically what recursive call is, in which you're calling a function within a defined function block by the same name. So, but the problem with this is we'll keep calling this forever and forever. So we have the def function. This function is gonna go back to this defined function and run this again, but you could start to see here that it's gonna run forever, and that is gonna be a problem. So that's where the base case comes in, which is the condition for when the recursive process should stop. So that's basically how we format recursion in Python. So the first program I'm going to be making in recursion is a very common example for the first recursion program we're going to be making. So the first recursion program I'm going to be making here is a factorial program. Now recall what a factorial is you're basically taking a product of a number times its preceding integers. So for an example, if you have 4 factorial, that essentially means you're doing 4 times 3 times 2 times 1. So in this case, you're taking the 4 and you're multiplying it by its preceding integers. So 3, 2, 1. And when you're doing factorial of 5, you're basically doing 5 times 4 times 3 times 2 times 1. And recall here that we're stopping at 1. If you do times 0, then this whole thing is basically going to be 0. And that's why we are stopping at 1 in this case. So, and here it goes so on and so forth. So the first step that I actually want to do in making the factorial program in recursion is defining the function itself. So I'm going to say def, and when I say def, I'm going to have to define the function. So in this case, I'm going to say factorial. And yes, the purpose of this program is to identify the factorial of a number. So since this factorial, so the user is going to be passing an argument to this factorial function, which means that the argument is basically going to be the number that you're trying to take the factorial of. So in this factorial parentheses, I'm going to specify a parameter that the user must pass in. The argument that the user must pass in is basically the number that you're trying to take the factorial of. You're doing def factorial n. So the first step that we want to do is find the base case. So the base case is basically the simplest case that you can find in regards to a problem. So what would be the simplest base case, or what would be the simplest condition to a factorial? Well, if we put a comment down here, and let's start off with the first factorial. So 0 factorial equals 1, and 1 factorial is equal to 1, right? If you keep moving on, however, so 2 factorial is equal to 2 times 1. This is where we actually start to see things recursively, right? We see here that these are two of the simplest cases, but when you start to increase the numbers, now we start to see where factorial is happening. So we see factorial starting at mainly 2, and so on and so forth. So 3 times 2 times 1. So we can see here that the simplest case actually could be 0 factorial or 1 factorial. And therefore, we established that this is the base. These two can be the base case. But in this case, I'll be saying if n equals 0. And that's basically what base case is. Finding the simplest solution to a problem, or finding the simplest condition to a problem. So in this case, the simplest condition to the problem is 0 factorial. But at the same time, this is the case in which the recursive call should actually be stopping at. So the first case I'm going to be writing here is an if condition. So recall, a condition allows the program to make decisions. So if I say if n equals 0, which means this is the simplest case we have in terms of a factorial. So if n actually equals 0, then what this essentially should return is 1. Since 0 factorial is 1. And now this is our base case. This is the simplest condition for the factorial, and this is also at the same time the condition for when the recursive call should stop. So if you didn't have this, and if you try to take the factorial of a number, and now recall here, if you have 3 factorial, then we're basically doing 3 times 2 times 1. But if you don't have a base case, then what this is going to do is 3 times 2 times 1 times 0 times -1 times -2. And we don't want that. We want to stop at a certain point in a recursive call. And that's why it is important to include the base case when you're trying to make a recursive call. So now, next, we're actually going to be doing the recursive call. So how do we make the recursive call? Well, we see here that you have 0 factorial equals 1. That's a simple condition. 1 factorial is 1. Yeah. So 2 factorial is 2 times 1. 3 factorial equals 3 times 2 times 1. Now, it'll make more sense to make your recursive algorithm if you actually try out many examples. So you start to see the pattern of what is going on. So 4 times factorial is 4 times 3 times 2 times 1. 5 factorial is 5 times 4 times 3 times 2 times 1. Now, what is the pattern here? If you look at 5 factorial, right? This 5 factorial is 5 times 4 times 3 times 2 times 1, right? But if you look above, this 4 times 3 times 2 times 1 is the same thing as 4 factorial. So in this case, I'll be replacing this 4 times 3 times 2 times 1 with 4 factorial, which is basically 4 times 3 times 2 times 1. Now let's look at this comment. We see 4 factorial is equal to 4 times 3 times 2 times 1. So we have to look at the comment, we have to look above and see that 3 factorial is 3 times 2 times 1. Now in this product, we have to find where 3 times 2 times 1 is. We see here that 3 times 2 times 1 is indeed part of this 4 factorial. And we see the common here. So 3 times 2 times 1 is basically the same thing as 3 factorial. So in this case, replacing 3 times 2 times 1 with 3 factorial. And now we look at 3 factorial. So now we have to look at the common product. So we see here 3 times 2 times 1. If you look above, we see this is a common. So in this case, I'm going to be replacing 2 times 1 with the 2 factorial. And let's keep moving on. So 2 factorial is equal to 2 times 1. We see here 1 is above. So I'm just going to replace this with 1. But we see here that 2 times 1 factorial is basically 2 times 1. And now we can stop at that point. But if we keep doing -1, we see that we see that there's going to be a flaw. So that's why we want to have the base case. We don't want to keep moving on. We don't want to have an infinite recursive call. We want to stop at a certain point. And a term for this is, if you have infinite recursion, there is an error called Stack Overflow error. And that basically means you're having infinite recursion or a recursive call that is calling itself forever and ever, and there's no ending to it. So that's why it is very important that we have a base case to this. So now we're starting to see the pattern here. Let's actually implement it. So in this, I'm just going to have an else. So if this condition isn't reached, then we're going to run this. So the way we're doing this is, if we start at 5, for example, then we see here that it's going to be basically 5 times the factorial of its preceding, 5 times the factorial of its previous integer. So if you take the factorial of n, then we're basically doing, let me put a comma here, we're basically doing, so n factorial is basically n times and n minus 1 factorial. And basically, we see here that we can make a recursive call to this factorial right here. So that's the way we can visualize step by step how we can implement our recursive algorithm. So if n equals 0, that's the simplest case. This is the recursive call. Now let's follow this example. So that's an easy thing. That's an easier way where you can visualize many examples for a problem. In this case, factorial. And you can find a pattern among all of these examples. And you can see here that it makes it a little bit easier to actually implement your recursive algorithms. So now I'm going to follow this format. N factorial is equal to n times the factorial n minus 1. Now let's translate that to code. So n factorial is basically n times. So n times n minus 1 factorial. So let's translate this function here. So n minus 1 factorial is the same thing as saying factorial and in parentheses n minus 1. So now I'm going to write factorial n minus 1. Right, so now we have our complete defined function for the factorial recursion. So now I'm going to be testing. So first I'm going to print out factorial of 1 in this case, which should output 1. Recall here that this defined function is going to return a value, and I'm basically printing out that value. So if I print out factorial 1, it's going to print out 1. If I do print factorial of 0, then it's going to print out 1. Because if we pass in the value of 0 here, we see here that the termination condition is already there, so it's going to return 1. But if you say 1, then we're going to call this factorial 1. This condition isn't true, so it's going to go to else. Let me show this through comments so it's easier to understand and visualize. So if you say, I'm just going to get rid of this. If you say factorial of 1, that's basically saying, it's basically returning 1, following this recursive call. So it's following 1 times factorial of 0, and now we're going to be calling factorial of 0. So now in a new line comment, I'm going to say factorial 0. Then it's going to go back to the defined function and now pass in this argument of 0. And now we see here, if n equals 0, that basically returns 1. So factorial of 0 equals 1. And basically this evaluates to 1. And therefore we can see the answer in this case is 1. If I do factorial of 2, that should print out 2. If I do factorial of 3, that should print out 6. If you do factorial 4, then it should print out 24. And so on and so forth. You can test for more cases. But we start to see here that it's easier to implement your recursive algorithms if you write out all of your examples and you visualize and you find a common pattern that you can identify within all your examples. So you see here factorial 5 is 120. I'll just write this out through code or comments so that it's easier to understand. So if I do factorial 5, that essentially means you're doing 5. Well, first of all, it's going to check out this condition. N equals 0 is not true. So it's going to check this else or remaining condition. So factorial 5 is equal to, we see 5 n. So 5 times factorial of 5 minus 1, which is 4. So now it's going to call factorial 4 back in the defined function. And I'm going to give a new line comment. So factorial 4 is basically equal to 4 times factorial of 3. And it's going to keep going on until it reaches the base case. Factorial 4 is 4 times factorial of 3. It's going to go back to our defined function above. And now, in a new line of comment, I'm going to say factorial 3 is equal to 3 times factorial 2. And the rest would seem pretty familiar. If I write out the rest, you see the pattern here. It's factorial 3 times factorial 2. And factorial of 2 is equal to 2 times factorial of 1. Now we're starting to approach 0, which is when the recursive call is going to stop. 1. And now we slowly reach towards factorial of 1, which is 1 times factorial of 0. And now, factorial of 0, when you plug in 0 into this function, it's going to return 1. So factorial of 0 is 1. So now I'm going to go through each of these. I'm going to go from bottom to top of each of these comments and substitute in the values of what we evaluated here in the base case. So the base case is that factorial of 0 is 1. So wherever I find it above factorial 0, I'm going to replace it with 1. And now factorial of 1 is 1 times 1. So that is 1. Now we're going to look above and see factorial of 1 and substitute 1 for factorial of 1, which is what we evaluated here. So factorial of 2 is 2 times 1, which is 2. Now we're going to look above and see where factorial of 2 is. So factorial of 2 is here. And since we evaluated below that factorial of 2 is in fact 2, we're going to replace that with 2. And factorial of 3 is 3 times 2. So 3 times 2 is 6. And we keep moving on until we reach what we want to evaluate it here in this case. So here factorial of 3 is 6. So factorial of 3 is 6. And I'm just doing this so it's easier to actually visualize how the process of recursion works. And this is the simplest example that I gave in recursion. But you'll slowly start to get an idea of how you can implement your own recursive algorithms. So let me finish this. So factorial 4 is 4 times 6, which is 24. And lastly, factorial 4 is 24. So now we're going to replace this with 24. And 24 times 5 is, in the end, 120. So that's basically what the process of recursion is we have a function that is calling itself over and over again. It consists of two important aspects. The base case, which is the termination condition for the recursive call, as well as the simplest case that you can find for a problem. And the recursive case is actually the function that's being called over and over again until it reaches the base case. So now that we covered the concept of recursion in this video, in the next video we're going to be covering command line arguments.